Hello everyone, my name is Enzo Tartaglione and today I'm going to present you a work titled Compressing Explicit Voxel Grid Representations. Fast NeRFs become also small. As the title suggests, this work will present a technique which we call re-NeRF, which targets the reduction of the model's size. In particular, why do we need a method to reduce NeRF sizes? The original NeRF, which was proposed a couple of years ago, was very compact, counting a few megabytes, even tens of megabytes, but it was very slow in the rendering process. Recent very fast NeRFs being proposed had what they called explicit voxel grids. Out of this, we can mention EVG-O, PlenVoxel, TensorRF, and many others. But they have a drawback. They occupy a lot of memory. Many approaches in the literature tries to enforce sparsity, but in order to enhance rendering quality. Out of this, for example, PlenVoxel. re-NeRF is the very first approach on EVGs which targets the reduction of the storage memory, virtually applicable to any EVG-NeRFs. How does it work? Well, with re-NeRF, we target compressibility of the model, and we make it applicable virtually on top of any EVG-NeRF. In this respect, we work at the level of voxel grids only. We do not work on the MLP part. In the proposed approach, we have a first phase in which we remove voxels using first-order Taylor expansion for the loss. And we have a feedback mechanism which is in charge of correcting underestimation for the first phase and enforces also a geometric prior on the grid. For the selection of the voxel to remove, we resort to first-order Taylor expansion for the loss function used for the training. Let Wi be the parameter associated to the ith voxel. If the estimated perturbation in the loss value is sufficiently low, then we can say that the ith voxel is not significantly contributing in the rendering, and we can remove it. However, we need to keep in mind that the aforementioned evaluation is just approximated. It can happen that it was underestimated and the loss increases by a higher value than expected. And its reintroduction is suggested by a high value for the gradient. In that case, we reinclude the voxel if and only if also another condition is satisfied. We reinclude a voxel if it is a neighbor for another voxel already in the model. In other words, if a voxel wants to be reincluded but is isolated, then it will not be reincluded. Take the figure as an example. In red, we have the voxels in the model. In green, the voxel with a high gradient, which wants to be reincluded. And in blue, the candidates for reinclusion, which are also neighbors for voxels already in the model. Intuitively, we need to iterate this research process in order to find all the connected voxels satisfying both the conditions. In general, we iterate between the phase of removal and the reinclusion, and they are governed by two hyperparameters: gamma, which tells us how much to remove, and delta, which sets a threshold to reinclude. Looking at the main results, we observe for the EVG-O, TensorRF, and PlenVoxel a significant reductions in model size, particularly effective for the EVG-O, which is essentially no performance loss. We propose here two compression regimes: low, which is more conservative, and high, where the maximum worsening tolerated is of at most 1 dB. Looking at some rendered images, even with high compression, we observe essentially no degradation for the high frequencies. More visualization are available in the supplementary material. To conclude, re-NeRF is successful to remove a large number of voxels with little or no drop in performance. This approach is applicable to virtually all EVG-NeRF approaches. The reinclusion feedback mechanism minimizes and prevents the quality and degradation for the rendered image. And as future work, we want to integrate re-NeRF with also a quantization mechanism. Thank you so much.